Hi everyone. In today's video, we are going to talk about an important application of RNN, which is usually called as a machine translation, where we consider an input statement, which is the source statement, and we convert it into a destination statement in some other language. Just to give an example, this is an example of a statement which is written in English, like reason with logic, and its Hindi translation is written over here. Now, there are some obvious challenges which we can face while modeling this sort of problem. One of them is the fact that the size of input and output statement are not exactly the same. On the top of it, the way we model such problems is like this. First of all, there is going to be an encoder layer which takes into account the input statement, and then with every input statement which we have, there is a stream of hidden layers which are being created. And this is actually, if you see the architecture of a vanilla RNN, a hidden layer is created over here. Now if I see the architecture of an LSTM, I am just going through the past videos. There is a hidden layer created over here as well in the form of ST, as well as in the form of the GRU, which we discussed last time. There was a hidden layer as well. So hidden layer is something which is definitely going to be created before we are even making an output. So this application or this entire encoder decoder architecture will take into advantage the hidden layer created out of the encoder, passing it to the decoder, and using the hidden layer of the decoder as well to give the predictions which kind of look like this. So while we do such a prediction, it might be possible that the relative words may not be aligned properly. For example, if I have to predict this first word, which is Tark over here, so if I see the entirety of the three words, there is like reason with logic. It's like with is not a direct translation to Tark. A combination of reason and logic is. So maybe at one point of time we should be knowing the hidden state corresponding to which word should be given more preference as compared to other. Over there, this attention mechanism comes in handy, and how it is exactly done, we will be explaining it entirely in this video. So as of now, just for numerical convenience, what we do is we have three letters in English, reason with logic, or three words in English to be more precise. We associate a hidden state corresponding to it. We assume that there is an RNN, and the first output of the RNN is actually a hidden state which we are getting over here. So this is the hidden state, and we are assuming that in the hidden state there are four nodes, and hence the encoding is a vector of size 4 cross 1. Like it is a vector which is like 1 cross 4 over here, but when we will perform the calculations, it's 4 cross 1. Now width is again another hidden state. Like width is determined on the basis of the hidden state H1E of the encoder. Like reason came first. Based on the hidden state generated by reason, we generate the hidden state corresponding to width, and this is the encoding which is coming in out of the width statement, like with word, and it is again a hidden state with four nodes, and this is how it will be looking like. So ideally these are some values which I have put in, but if you remember the architecture of vanilla RNN, it ideally was looking like this. We have HT, we have W times FT minus 1 plus U times XT plus B, like this. We have this XT over here, we have U over here. W will be a parameter which will be calculated in forward and backward pass, and this is actually HT minus 1. I wrote it as if yeah, HT minus 1 is the hidden state corresponding to the previous state, and B is the bias. So based on that, this is exactly how the encoding corresponding to each of the word will look like, and this encoding is of the hidden state. Now let's see how the dimensionality is looking forward. So as I have explained just above, this is how HIE is calculated, just that I used T in my previous examples. I will consider I over here for convenience. So we have xi to be of order vn cross I. Now what this means is we assume that our vocabulary is having some finite set of words. So let's say our English vocabulary is having 30,000 words. Let's say I'm assuming this. This is not exact figure, but around about 30,000 words are there. So we say that if the first word is reason, we consider a one-hot encoding of the entire 30,000 vocabulary and put 0 at all place except the place where reason is present. And we, so if this is the place where reason is present, 1 is put in over here, rest everything is 0. So xi is going to be a one-hot encoded vector of size vocabulary into 1 because it's corresponding to one word only. Now, in order to make sure that the hidden state, and also I just specified that there are 4 nodes in hidden state, we are proceeding just like the example we discussed in the previous video. Like, we first consider the vocabulary and we create the xi dimensionality, and we then take into account the hidden units in each state, which is like 4 over here. Then we say that hi minus 1e is of order 4 cross 1. Now, in order to make the calculations permissible, we see that U could be of order 4 cross V input, while WE is of order 4 cross 4. The detailed explanation of the entire thing, why these things are happening, are explained in part 4 of the video. And eventually we get bias of order 4 cross 1, and the activation function could be anything. So we are not bothered much about the activation as of now. It could be any value, and it is ideally a parameter which we will be tuning in real life application as of now. So what we observed is, we are just focused on encoder. We considered a vector which is like a one-hot encoded vector of the first word. Then we predict the first hidden state. Once we predict the first hidden state, we proceed further to consider the one-hot encoded representation of the second word, and we predict the second hidden state. We get the second hidden state, we proceed further, consider the one-hot encoded representation of the third word, and proceed to find out the third hidden state. And on completion, we get 3 hidden states which kind of look like this. Just remember that these are the hidden states corresponding to each word. For us, one-hot encoded vector will be more than enough to understand what the word represents like, but actually the meaning of the word and the different context with which the word is associated, that the model learns from successive forward and backward propagation, is exactly what is captured in the hidden state encodings as of now. So what we get is the hidden state and a vector corresponding to the encoding which it captured. Now we will proceed further, but before doing that, we will just look into the paper and see whether we are aligned or not. We will go to the page 2 of this paper. Ideally, this is what they have done. And the paper, they considered a vector of size x1, x2 to tx. In our case, tx is equal to 3. We have x1, x2 and x3. They considered ht, the hidden state which we are trying to find out at the encoder level, as a function of xt, which is like the input which is coming at time t, and ht minus 1. We exactly modeled this, and they commonly used an RNN over here. So what they are saying is, this entire f is an RNN. It's not an activation function like we use in our definition, but that's an RNN. And when we talk about RNN, this is exactly what we are trying to do. So we are pretty much aligned on how the things are in this paper. Like, first we consider an encoder, and then we try to find out the hidden state corresponding to each word. In our dummy example, this is not actually coming from any calculation, but just to put some placeholders to make the things easy, I have written the encoding of this form. And actually this is not going to be used if you do the actual neural translation. So now we proceed further, and then we realize that, okay, we have to predict a word, Hindi word, which is Tark. And we say that the start word corresponding to Hindi is like this, start of sentence, or anything like the start of sentence will be there, and the hidden state at the start of sentence is this. And we consider that the hidden state corresponding to the Hindi translation is having 3 nodes, and hence a vector having 3 components. Now we need to predict this word in the first place. So this is how we will proceed. So we will multiply. So h1e, what we have got in the previous step, is a vector of order 4 cross 1, right? So in encoder, we were having vectors of order 4 cross 1, which is shown over here. Now the decoder will expect the vectors to be of order 3 cross 1. Like this is the hidden state. It is of order 3 cross 1. Now we will try to transform the vectors of order 4 cross 1 to 3 cross 1 in the first place, which we did by considering a weight matrix of order 3 cross 4. So this is the trick. Whenever you see a mismatch, you always impute a matrix of a suitable dimension which will be tuned while you do the model tuning or you do the backpropagation. Just that the process while you do the backpropagation will be a bit slow, and ideally the values of the tokens are pretty much high in real terms. So it is not actually a problem when you are trying to solve it in real sense. But over here, since this is just a toy example I picked up, and also like 3 or 4 vocabularies are there, not more than that. So I considered a matrix of size 3 cross 4 just to make sure that this h1 cap e, like h1e, this one is of order 3 cross 1. Now we do a linear transformation between the matrices which we have obtained and the hidden states which we have right now. So as of now, from the encoder part, we have h1 cap e, we have h2 cap e, and we have h3 cap e. And for the decoder, we just have s0. We are yet to find out s1. The way we need to find out s1 we will discuss, but we are yet to find the value of s1. We have only these three values, like these and this. Now we will represent it in the form of a linear combination to find out Z1. We say that we consider a matrix W encoder. So this is W encoder. H1 cap E will be considered. This is a W decoder, weight corresponding to decoder, and this is S0 which will be considered, and then we will be finding out a value called as Z1. As of now, since we had only just one hidden layer, it is like 1 cross 1 only for us. Like these are all scalars. W encoder, W decoder are scalars, and also these are again the parameters which will be tuned in the course of time when we are performing a backward propagation. So we proceeded till now like this. First of all, we were having three English words. We put them in the form of one hot encoded vectors to our RNN network, and we were able to get the hidden encoding or hidden layer encoding corresponding to each of the words, which look like this. And then we realize that the decoder will be needing a hidden state which is having like three hidden nodes. And then we consider a weight matrix. We normalize the hidden states from the encoder to be of the same dimension as the hidden states of the decoder, and we express both of them as a linear combination of each other. Now, since we have find the values of Z1, Z2, and Z3 over here, we will proceed with one of the important steps as mentioned in the paper, which is finding the values of alpha i's and eij's. So over here in the paper as well, they considered the hidden states in the encoder, and based on the different hidden states, they assigned a preferential weightage to uh, put as an input to the decoder step. So the end goal of the decoder RNN should be looking something like this. But as of now in decoder, we just know the Si minus 1, Yi minus 1. We don't know the value of Ci, as they have mentioned in the paper over here. We are looking forward to find the value of Ci, and Ci ideally looks as a context vector, which they have mentioned. But we will be coming to it slowly and gradually, and these things will start to make sense. So as of now, we were able to get these Zi's, and we are able to get the Eij's in the form of a matrix multiplication being done. As of now, VA is a 1 cross 1 vector only, because we have an output of size 1 cross 3, and then I guess, yeah, so one, not 1 cross 3, 3 cross 1. So then we proceed forward to the calculation of alpha ij's. So now this is ideally what is mentioned in this paper, which will mean that corresponding to each of the annotations or corresponding to each of the hidden states. Like we have how many hidden states? Three hidden states over here, like H1E, H2E, and H3E. We need to find the preferential weightage corresponding to three hidden states. That's the end goal which we are trying to do. So instead of passing multiple hidden state, we are going to pass one unified hidden state to the decoder layer. So this is what we do. We have found out E11, E12, and E13. We try to normalize it by using softmax, and this is exactly what is called as a Barnou's attention, which you guys have been seeing a lot in TensorFlow as well as in other applications. So this is how the attention is going to look like. We calculated Eij, this A times Sihj over here. um, I think let me highlight it. Yeah, this one we calculated using this the e function which they were talking about. I considered it as a tan hyperbolic multiplied with a vector, which could be a scalar as of now, but it usually takes form of a vector only. And then once we have multiplied it, then we use the softmax criteria to normalize it. On doing so, we get values like this: alpha 1 1, alpha 1 2, and 3. And ideally these are supposed to be probabilistic values only. Let's say I get the alpha 1 1 as 0.7, maybe we get it as zero point 0.2, and we get it as 0.1, alpha 1 3. And what we do, we express the encoders as linear combination of these alpha values to get the context vector, which looks like this. Now this is the context vector I'm getting. So just check, this one was H1E, which I copied from here. This is the H1E. This is H2E and H3E. I write it over here. H1E, H2E, and H3E. These alpha i's are calculated using the formula mentioned in the paper, and then eventually this is the context vector, which actually goes in the formulation of S1 in the decoder in the following way. Now let's go to the paper and try to correlate what we have actually done, and the final diagram I will draw with the example as well. So we were having the H1, H2, H3. These are the hidden states we were having. If I focus on the diagram on the right side, and then we were able to calculate these weightages, which are actually percentages as to how much percentage of weight must be put on a particular hidden state as compared to others. We were able to calibrate everything in the form of one unified vector, which went actually in the prediction. So instead of passing like 4 5 different vectors, like in our case we could have passed 3 different vectors and then told the model to pick out, or the train the model to find out which one is a relevant one, or we can pass the latest hidden vector and allow the model to train itself on finding the translation. What we did over here is just we found out the unified context vector, which is Ci, and we are going to pass it in the form of model. Now let's see how we are actually going to do it. So it will proceed in the same way as we have done previously. So S naught is the start of the sentence of the decoder, which is usually of the form SOS, or start of sentence we call it. And corresponding to SOS, there is definitely a state which was assigned. I think SOS was like this: 0.3, 0.4, and 0.1 over here. So S0 for us is of form 0.3, 0.4, 0.1. This is a vector of shape 3 cross 1. And if I consider y naught is going to be again a one hot encoder vector. Let's say the vocabulary of Hindi is 20,000, and the start of sentence is coming somewhere over here. It is 1 and 0 elsewhere. This is like start of sentence, and whenever the sentence ends, that will be end of sentence, but that's the start of sentence. So this is the vector we are passing. This is again the parameter we will be tuning, yd and ud, and we passed a context vector as well from the previous step, and this is the extra parameter. So this is the extra term which we are adding while we are trying to figure out the RNN for the decoder part, and bias term will obviously be there. This is what the author meant when he said that while doing the hidden state prediction for decoder, we will need the hidden state of the previous time step, the previous predictions which we put in the form of one hot encoded vector and the context vector at that point of time. This is how we proceeded with doing it, and on doing so, this is the entire dimension set which I was able to find out. Y0 was was of form V out cross 1, which is like 20,000 cross 1 only. We assume the vocabulary of Hindi is around 20,000. UD is of order 3 cross 20,000, or vocabulary output. That's how the multiplication will make sense. S0 is of order 3 cross 1, we have found out. WD will be of order 3 cross 3. Now we know C1 is specifically of order 4 cross 1 because this is how C1 was calculated and it looks like. To put it in the form of a 3 cross 1 vector, we will need WA to be of order 3 cross 4. Then only it will get multiplied with a vector of order 4 cross 1 and we end up with 3 cross 1. And the bias is usual 3 cross 1 only. Now, since we have found out S1, the output step remains as it is. There is no change whatsoever in that. The value of S1 will remain as 3 cross 1 only, and the value of V is going to be of vocabulary output cross 3, like 20,000 cross 3 in our case. If we assume it, I believe these are not the exact numbers, neither 20,000 or 30,000. The vocabulary might be much more intensive than what I am anticipating. So as of now, just to fill the place of V out, I am just putting 20,000 over here. So V will be of order 20,000 cross 3, S1 will be of order 3 cross 1, and C is of order V out. And this C is not the context vector, this is a bias, right? This is like a bias term. So is it of order V out cross 1? So that's all. So once we do that, we get the predictions in the form of a softmax, which comes out to be this. So ideally, we will get a prediction like this: 0.001, 0.002, something like this. Then we see that 0.8700 something, 0.07, like this. We see the maximum value is happening over here. We find the lookup for that, and we kind of find out that this is the word which we were looking for, and it was able to predict it. Now this happens after like a significant amount of iterations in forward and backward propagations are done. So then we are able to get the first word which should be there. So we considered, so this is the flow which went in. We considered an English word completely, and then based on the understanding of the English word, we predicted the first word, and based on the understanding and all the parameters we have found out for the first word, we went ahead to proceed Y2. Now overall, the entire architecture will look like this. It's a big architecture. I'm showing you like step by step. This is like the encoder stack over here, encoder stack over here. So we calculate the hidden layers for each of the word, reason with logic, and the way to do that I have explained previously. Then we proceed forward to calculate a context vector by assigning different probabilities to different hidden states. And on once we have got the context vector, we proceed with the evaluation of the decoder. Like it is the start of the sentence at y0, at y1 we get this as a word. Then the decoder will take into account all the things which we have calculated over here. Like we have calculated this one over here, recursively use it to predict the next word, and so on. So this is how a simple attention model works, and this is exactly what is explained in this awesome paper, which you can easily find out from archive. I will reference this paper in the description set, and they have given some results as well. This is exactly what I was talking about. Like they have made a little bit of translation, and this attention network actually enabled them to visualize where exactly the word which they are trying to predict is being focused on the source sentence, and so on. And over here we didn't needed the source and target to be of the same size, a drawback which could have been there when we are doing a statistical machine translation. I urge you all to read this paper because it's a very interesting read, and try to draw parallels between what we did in this video as well. So that's it from my side. Thanks for listening.